force and work. Okay, so force and work. So work is a big part of these physics application problems. We do lots of problems where we're calculating the total amount of work to do something. So the basic formula for work is force times distance. So if I push this table across the carpet to the wall, okay, I'm going to have to apply a force to do that. I'm going to have to continue to apply that force over that distance. The farther I push it, the more work I have to do. Okay? The heavier the table, the more friction on the ground, the more work because I'm going to require more force to push it. So if I were to push that table to the wall, that would require some amount of work on my part, which is a function of how much force I'm applying, and then how much distance I have to apply that force over. So the work is force times distance. But what if we have something, and this is typical, where as I'm doing the work, the force is continually varying. So the force doesn't stay constant. Okay? So suppose I'm pushing this table and the floor is kind of wavy, right? So whenever I'm pushing uphill, it's going to require more force. And when it's kind of going downhill, it's requiring less force. So that force is continually changing over the distance. So how are we going to calculate the work then? If the force is some function that's changing as the distance over the distance in question. So what's that going to require? So application of what we've been doing all semester. Yes, right. So we're going to take this. We're going to sum up a bunch of little bits of work, right? So if I get the work for just a little distance before the force changes, for the most part, I can get that little amount of work, and then the next little amount of work for the different force, and the next little amount of work for the different force, and so then we're going to sum up all those little bits of work. And what's that principle? Summing up all the little bits of work to get a total amount of work. You should be thinking integral. You should be thinking integral. So total work is going to be the sum of little bits of work. Or we could write it this way. Okay, so to understand work and set up these work integrals, we got to know all about force. Distance is pretty straightforward, right? Distance is, you can think of a little change in distance or a big change in distance is pretty straightforward, but force is more complicated quantity. And so to set up and understand work, we got to understand force. So let's talk about force. Okay, so it's kind of different in metric versus English in terms of calculations and what happens. Okay, so force is mass. So what force is accelerating a mass, right? So to accelerate something, that requires force. So force is mass times acceleration. But this formula we're going to use primarily when we're dealing in metric units. We won't really see this formula in English units, and I'll explain why in a second. Okay, so what is force? Force is what you have to do to accelerate something. What you have to do to accelerate it. Change its position or change its speed from a constant speed. Okay, that's what force is. So it's mass times acceleration. Okay, the mass should be in kilograms. Okay, so that's an easy conversion. But mass is in kilograms. Acceleration is in meters per second squared, and then your force is kilogram meters per second squared, which is the unit newtons. Okay, so this is our force overview here for metric units. So gravity creates a force on all objects. All right. So what is the force of gravity on an object? What is that called? What is the force? Anyone know? What is the force of gravity on an object? It's weight. That's what weight is. Weight is a force. Whenever you're talking about weight, it's a specific kind of force. It's the force of gravity. Weight is a force. Okay? So the acceleration that we use then is g. That's the constant for our gravity. So that's 9.8 meters per second squared, or 32.2 feet per second squared in English units. So weight is force. It's just a specific kind of force. It's the force of gravity on the object. And so then when you're talking about weight force, the acceleration is the constant acceleration if we're on Earth, right? So this is for Earth. Okay, so weight, since weight is force, it's going to have the same units as force units. So in the metric system, weight is newtons. And in the English system, it's pounds. So pounds is the English unit for force or weight. So weight is a type of force, we said. So here's the deal. In the English system, we usually don't use mass, okay? So we just talk about weight. Really, mass doesn't usually come in at our level to the problems that we're going to do. If it did, it would be the unit of mass in the English system is called slugs. And probably most of you have never heard of that before, and that proves my point. It's not really used. In the English system, we don't talk about mass. And so instead, in the English system, the whole conversation will be about force values and thus weights. So you'll just talk about pounds. So you won't use the formula MA or mg in the English system. You'll just have the weight or the force in pounds. Now in metric system, often things are given in kilograms. And if they're given in kilograms, then we have to use F equals MA or F equals mg to get the corresponding Newton force for the kilograms. So like when you have often in these problems in the metric system, you'll have like an extra step to get from kilograms to newtons. When you're in English, it'll just be pounds, and you won't have that extra step of using the F equals MA or F equals mg. Does it make sense? Okay, so that's an overview of force. Okay, that's an overview of force. And remember that weight is a subset of force. It's a type of force. Okay, so for weight, we're going to use newtons in metric, and we're going to use pounds in English, because those are force units. Okay, so let's talk about, so here's this, what we talk about. Total work is the sum of little bits of work. That's the principle at hand here. So springs. So springs, what happens with a spring? The further you stretch it, the more force it takes to hold it in that stretched position. So if you just stretch a spring a little bit, it doesn't require much. But when you stretch a spring a large displacement, now it's pulling back with more force. Okay? So the force to hold a spring at a displacement x is k times x, and k is the spring constant. So it's basically a number that reflects how stiff the spring is. If that's a high number, then it takes a lot of force to move that thing. That would be like think of a strut or a shock in your car. That would have a very high spring constant. And what would have a very low spring constant? Like a slinky, right? A slinky is like a spring that has almost no resistant force at all. That would have a very low K. Okay? And so then X it's the displacement from the natural length. So it's not the length, but it's how far you've stretched it from just natural length. So if the spring is just sitting there, has no force on it, it's just allowed to just be at equilibrium, that's called its natural length. That X value is now, from that how much we stretch it from that distance. Okay, so I'll draw that real quick. So if I just have a spring and I lie it on the table, that's called its natural length. There's no forces on it. It's allowed to just be the length that it is without any outside force. Okay? Now I come along and I hold one side and I pull the other side. And so now say it looks like this. So this is the worst spring I've drawn all day. Okay? But what is X? X now, this is X, the displacement. X is not the new total length of the spring. X is how much I stretched it. Displacement. Okay, so a force of 40 newtons is required to hold a spring that's been stretched from its natural length of 10 centimeters to 15 centimeters. How much work is done now in stretching it from 15 to 18 centimeters? Okay, so we've got all the information we need to tackle this here. And so what happens when we stretch it? Say we're holding it at 15. What happens to the force required as we stretch it from 15 to 18? Yeah, the more you displace it. F equals kx tells us the greater the displacement, the greater the force. So as soon as I pull it a little bit, now the force just changed for me to hold it there. Pull it a little bit more, and now it's requiring more force. So we can't just simply do, work equals force times distance. Why? Because the amount of force is continually changing as I'm pulling it. So what does that mean? It means that the total work is going to be calculated how? As the sum of little bits of work. So starting from 15 centimeters, it's going to take some force, and I can move it a little bit and assume a constant amount of work for that little bit. And then the force increased a little bit. Now I'm going to move it a little bit again at assumably a constant force again. And so I'm going to think of moving it in little chunks at a time with a constant force at each one of those little changes. And so then I can get little amounts of work and add them all up. Okay, so to get these forces, we need K times X. That means we need K. So I need to get K for the spring. That should be easy. How do I get K for the spring? Well, K, so I need some displacement and some corresponding force, and that will give me K for the spring. So do I have a displacement and a corresponding force? Yes, what's the displacement? 5. When X is 5, the force is 40. Therefore, I can get my spring constant, which is 8. And what's the units on 8? Newtons per centimeter. Because the 5 is centimeters. Okay, so I think we can just, so I put newtons per meter, but if we're consistent, we can just work this whole problem in newtons and centimeters as long as we're consistent with all our units. So we'll try that. We'll say the K for this is 8 newtons per centimeter. Okay, so now we're going to stretch this thing from X equals what to what? From 15 to 18? X is displacement. So what's the initial displacement and what's the final displacement for the work calculation? It's going to be 5 to 8. So we're going to displace this starting at 5 centimeters displacement to 8 centimeters displacement. And what do we need? We need a little bit of work. Typical amount of work. And what is work? Our work is our force times our distance. So the typical amount of work is going to be force times distance. And to get a little amount of work, what kind of distance are we talking about? In order to assume and able to calculate a little amount of work, we have to assume what kind of distance. If I stretch it a great distance, the force varies, right? The force varies over that distance. So in order to assume a constant force, what kind of distance am I talking about stretching it? Very small, right? Very small. As soon as I stretch it any considerable amount, the force is going to change over that, and I can't calculate the work. I need a constant force. So the only way I can think about having a constant force here is if I stretch it just a very small amount of a small distance, and then I'll assume a constant force for a very small amount of distance. So what is that? Delta D, or delta X, right? A very small change in the displacement. Now I can assume a constant force and get a little bit of work. So what is the force? Well, the force is Kx. What is my K? 8. So force is 8. There's my force, 8x. And then my distance is going to be a little bit of change in x. So I should be writing like delta W here. Okay, so delta W is going to be force times a little change in x. The force is always 8x, 8 times whatever the displacement is, and then I'm going to increase that displacement just a little bit so I can assume that constant force and get that little amount of work. So that's our, just like we did, typical element, typical volume element, typical strip. We have a typical amount of work. Typical amount of work is 8x delta x. And then how are we going to get the total work? We're going to sum up all the little bits of work. And the little bits of work are 8x with a really small change in distance. Infinitesimally small, right? And then from x goes from what to what? We said? Starting at a displacement of 5, ending at a displacement of 8. So, think about the approach. Think about the approach. We're going to get a typical amount of work, just like we got a typical volume of a typical pancake, or area of a typical strip. Now we're going to get a typical amount of a little amount of work, and then we're going to add all those little amounts of work up. Remember, look, dx is part of the math, right? Work is force times distance. That's the distance part. Dx is that little amount of distance. Dx is part of the math here. It's not just an afterthought telling us we're differentiating or integrating with respect to x. No, it's part of the math. It's the distance that's going to join up with the force to give us a little bit of work. And we're going to sum up all those bits of work from 5 to 8. And then our answer will be in what? What is work units? It's force times distance. Let's just do this real quick. We get, what, 4x squared from 5 to 8. So 64 times 4 minus 100. That should be easy to do in your head. 64 times 4, 128, 256. 156? Did I do that right? 156. And so what are the units? For work is force times distance. So this would be 156 Newton centimeters, because we stayed in centimeters here. And so if it were Newton meters, it would be 1/100th of that. It would be 1.56 Newton meters. 1.56 Newton meters. What's that? Okay, questions on this example? Yeah? No, you can't. Because that's displacing, that would be displacing it from 15 to 18. And that would that require the same amount of work? So if I was holding it at 15 and I stretched it to 18, would that require the same amount of work as holding it at 5 and stretching it to 8? Which would be more? Yeah, because once you stretch this thing to 15, it's requiring a lot more force than at 5. So from 15 to 18 would be a lot more work because your forces would be a lot higher because your string is so stretched out than 5 to 8. So if you do 15 to 18, you get a much larger number. It's a different situation. Other questions? Okay. So here's another type of work. So you got 20 kilogram chain, hangs 30 meters from the roof over the side of a tall building. How much work is required to pull the entire chain up to the roof? So as I'm drawing it, so always draw a picture. Okay, so always draw a picture and put your variables and your constant values in the picture. So you have a good visual to start with. So here's our building, okay? And initially we're going to have the chain is going to hang 30 meters. And so that's a really tall building. And that's a long, long chain, okay? And that so say that that's that, right? So say it's, and we're going to pull that whole chain up onto the roof. Why is this not a straightforward force times distance calculation for work? So why is this more complicated than that? Yeah. Right. So once we get some chain on the roof, now what about the force to continue to pull the remaining chain up? It's less, right? Because you have less chain hanging. So for every length that you get on the roof, now it requires a lesser force to keep pulling it up, and that just that force continually decreases as we get chain onto the roof. So here's that same situation. We've got the force is going to continually change as we're pulling the chain up. So that's going to require what? That's to get total work is going to require the sum of little bits of work. Okay, so let's we got to come up with some variables here. So what we'll say is we'll say that x is our distance down from the top. And so x is gonna mean the length of chain remaining hanging over the building. Length of in what unit here? Meters. So always define your variables very specifically. Don't use one-word descriptions of your variables. Be very specific. So then later in the problem, when you're dealing with those variables, you'll know exactly what they stand for. Okay? So x is the length of chain remaining hanging over the side in meters. Okay? And so what do we want? We want, if we're at x, if x is hanging down, so say this is all 30. This is 30 right here. What do we want? We want the little bit of work required to just move up, say, one link. When X is hanging down, we want the little amount of work. And so this is our little amount of work. So we'll do it in blue. And that equals force times distance. Again, a little change in X. If we change X too much, the force changes. So we assume a small change in X so that we can assume a constant force and actually calculate some work. Okay, so what is the force of X meters of chain hanging over the side of the building? What's another way to describe the force associated with X meters of chain hanging down? It's its weight, right? Its weight. So to hold it there is exerting the same force as gravity is exerting on the chain, which is its weight. So what is the weight? It's the force, and we're in metric units. So to get the force, we're going to do M times G. Okay, so is the mass 20? Our G is our 9.8. Or maybe I should ask this. Why is mass, why do I not just put 20 in here? Because this is the mass for X meters of chain. It's not the whole mass. We need the mass for any current value of X, right? For any current value of X here. So I've already pulled some up here. So the black is when it's all hanging down. But for a value X, only this much is hanging down. So I need the mass of X meters of chain. What's the mass of X meters of chain? (20 minus X). Is it 20 minus X? We need to do some math here, right? We need to do some math. 30 meters is 20. If 30 meters is 20 kilograms, how many kilograms is X meters? That's what we're saying. 30 meters is 20 kilograms. Then how many kilograms is X meters of chain? So really what we need is, what's the kind of the weight the mass density of this? How many kilograms per meter? How many kilograms per meter of chain?
So it'd be 20 by 30 minus the change.
So if we take 20 kilograms per 30 meters, if we break 20 kilograms up into 30 parts, we're going to get how many kilograms each meter is. And what is that? Is that 0.67? So every meter is 0.67 kilograms. So how many kilograms is X meters? How many kilograms then is X meters? Hope we know that. If 1 meter is 0.6 kilograms, then 2 meters is 2 times 0.67 kilograms. And 10 meters is 10 times 0.67 kilograms. So how many kilograms is X meters? 0.67 X. That should, if it's 0.6 kilograms per meter, and you've got X meters of it, you're going to take X number of 0.67s to get the total kilograms for X meters. Right? Every meter is 0.67, so then X meters would be 0.67X kilograms. So there's our mass. That's the mass of X meters hanging down. This is our G, and then that's our distance for the work. So we've got our little amount of work. Okay, so we're ready to set it up. Our little bit of work is going to be 0.67 x times 9.8 dx. Okay, and we're going to go from, so we're going to think of this backwards. So I oriented it this way so that we could go from 0 to 30 meters. So even though the chain starts at 30 and ends at 0, we think about adding up the little bits of work the other way. Okay, so we think about first the last little bit of chain, pulling that to the top. And then right before that, we have a little bit longer distance. How much work did it take to move that up a little bit? And then all the way down to 30, okay? Questions on this example? Again, you start by calculating the little bit of work. Start by calculating the typical amount of work in the given situation. And then we add up all those little bits of work. Okay, so if we wanted to avoid rounding error, we could just put 2/3 here. That's our kilograms per meter. Questions on this example? Anybody? Okay, so something harder. So now we got the same 20 kilogram chain, but there's a bucket holding sand, and then the bucket is consistently spilling sand as we pull it up. So we still are going to think about, having some chain up here and then how much chain is left, X amount of chain is left, but then we've got this bucket on here. And it's spilling sand as we go. It's spilling sand as we go. So that when all 30 meters, so let's talk about X and mass. So when X is 0 up here at the top, what is, or maybe just a little bit, like 0.00000001 meters, how much mass are we pulling up that last little bit? What is the mass that we're pulling up that last little bit when we're almost finished? Just barely right before we're finished. What is that amount of mass? And we can do total of bucket, sand, and chain. Total mass of bucket, sand, and chain right before we finish. What would it be? So the total of chain and bucket and sand is? So how much mass due to the chain right before we're finished? 0, right? Virtually there's no chain left. And then how about the sand and the bucket? When it reaches the roof, our mass is 5. Just read the problem, right? It says 5. Okay? And then what about when X is 30? When we just start, what's our total mass of bucket, chain, and sand? Hopefully that's not hard. Chain is how much? 20. Bucket and sand is 25. So total mass at a length of 30. 45. So if the sand is spilling out constantly and the chain has a uniform mass per foot or mass per meter, then we're going to assume that this 45 decreases to 5 constantly, okay? So at a constant rate. That 45, because certainly the chain will, we assume a constant mass per meter for the chain, and then if the sand spills out at a constant rate as we pull, then we're going to assume that this 45 changes to 5 at a constant rate. Okay, so again, we're gonna sum up to get the work. We're going to sum up all the little bits of work, so we need a little bit of work. Force times little bit of distance. The little bit of distance is so that we can assume a constant force. As soon as that distance is significantly more or has any significant length to it, the force is going to change, and we can't calculate work. We need a constant force, so that requires a very small distance to assume a constant force. Okay, so force is, it's the weight, it's going to be the weight of when the chain is hanging x meters over, right? So this is a function of x, so we could write that here. Force. And so what is this? This is the weight of everything when x meters remains. How are we going to get that? We want the weight, f of x, the force when x meters remains, is the weight when x remains. So how are we going to get that? So this next part is a very important part of lots and lots of these problems, all kinds of physics problems. And that's establishing, so mg, so g, so it's going to be m times g. G is constant, so which really comes down to what is the mass when x meters are hanging over the edge of the building. Okay, what is that mass? That's a function of x. So this next part is really important. So given an x, we need the mass, right? Given an x, we need the mass. And what's the relationship between x and mass? What kind of relationship is it? It's a linear relationship. This is huge. We're going to see these in all kinds of different physics problems. We need an expression that gives us the mass for any x. We need an expression that gives us the mass for any x. That's the idea of function, all right? And this will be like a linear function. There are different ways to come up with that. You just have to have a way that works for you. So can you come up with an expression that gives you the mass if you give it x? If you give it x, it will spit back out to you mass. That's what we need here. We need mass in terms of x. So in your math career, you've done things like this many times, way before calculus. So you've got to have some kind of method to do that. So I'm going to let you come up with that. All right? You will all do it different ways. But we need an expression that gives us m for any x. So it's an expression of m in terms of x. And that's going to be a linear relationship based on what we set up with that table there. Go.
That last interval from 0 to 30 seems like it should be negative, is because your delta x is actually negative. X is decreasing.
Okay.
So, like parentheses negative delta x if you're calculating the same
Okay.
as a positive one.
Yeah, I've never addressed that. I've just always set them up and gone from lowest to highest.
You know it should be positive.
Yeah, so it hasn't really
So I think
been an issue.
why.
That's what's happening. Yeah, you're right. I think it must be because I've gotten every sickness. I must be immune to the sicknesses. So it's like a headache. It's like sinus. So I think it's allergy. Yeah. I did on Saturday. I was out in my back and I was trimming these trees.
Yeah. Oh.
And
So they were trimming trees yesterday.
they have these little. The flowers are like these little buds of green things, and as soon as you touch them, they just explode into powder. So like my whole back is just green powder. It's all over the deck. I must have breathed a bunch of that.
Yeah, they trimmed trees yesterday. And had a horrible night.
Yeah, so I think that's what it is. Milligrams. Okay, so you may have done it differently. I got that for every meter that you pull this thing up, that number of kilograms is going to go down 4/3. Okay, so 4/3 kilograms per meter is what happens with this. And then I use this kind of point slope form of the line. I said that 4/3 times x minus 0 plus 5 is going to be that mass relationship. So it comes out to 4/3 x plus 5. That's what you should have gotten. And you might, if you could have done it a totally different way, that's fine. Somehow you have to, given two quantities changing together, and we need one in terms of the other, you need to have a method to come up with that relationship. So this is one example of that. So 4/3 x plus 5. Yeah. Sure. No, so it's positive because of the way I'm oriented x. So if I do 45 minus 5 or 30 minus 0, it is positive. So it's the way I've oriented my x. So according to how I've oriented x, positive going down the building, it is positive 4/3. Okay, so we got it. We got our little amount of work. Our typical amount of work. 4/3 x plus 5 gives us the mass at any length of chain x hanging over the edge of the building. And then that mass times g is the force to sustain. That's the weight force of everything hanging over the edge of the building. Times a little change in x gives us the little bit of work that I need. And then I'm going to add up all those little bits of work from, again, 0 to 30. Okay, these are the easy ones. These are the easy ones. Web work for Friday.